Hi, welcome back. We saw in the last video how the graph of the function for sine and cosine are developed and what they look like, and we talked about the properties of the natural sine and cosine, i.e. the unadulterated pure forms of these two functions. That's not always what we get to work with, so we need to talk about some transformations. And the first one I'm going to talk to you about is a change in amplitude. Remember that is the height of those peaks and valleys above the midline. So I have here my unit circle, but I've made it a little more flexible. So I want to change it to, and I want to remember what happens. As we go around that unit circle, we get, I'm graphing cosine still. So we get that curve that we would expect, right? Okay, so I just put a label on our y-axis to remind us that we're graphing cosine. Let's look at what happens when we make our circle bigger. So if I make my circle, say radius 3, or 3. Okay. Notice that this point, this green point at the top of my circle, is my starting point for cosine. So hopefully this shouldn't surprise you too much, because you'll remember that the coordinates of a point around a circle are, the x coordinate is r times the cosine of the angle that gets us to that point, and the y coordinate is r times the sine of the angle that gets us to that point. So it shouldn't surprise you, I hope, too much to see what I'm going to show you here in a minute, which is that our function looks very much the same, but it's taller. And in fact, I'm going to just put on here y equals cosine x. And now, so here's where it comes. The amplitude of the function is determined by the external multiplier. Okay? So you'll notice that these two functions are identical in shape. The primary difference is the height. In fact, that's the only difference. I'm going to make this one a different color. That will do. Notice they still have the same period. I'm going to pull these in here. Okay, so these two functions still have the same period. The green one, remember, what's the green one? The green one is, let's see, the green curve is y equals cosine x. The purple curve is y equals 3 cosine x. Both of these functions still have the same distance from peak to peak. Their periods are unchanged. What is changed, however, is the amplitude. So the function y equals 3 cosine x has got amplitude 3. This is not a coincidence. In fact, in general, for both sine and cosine, the function y equals b, I'm not going to use b, I'm going to use a, cosine x, or a sine x, will have amplitude equal to a. Now you'll remember that was related to the radius of the circle. So if you're asked to, for example, sketch the y-coordinate of a point that is rotating around a circle of radius 3, if you're looking at the y-coordinate, you're going to be looking at the sine. Okay, so you could do that. And we're going to, when I get done building all of these transformations, we are going to do an example here. So, up to now, my midline has been the x-axis. And that's because I've always put my origin in the center of my circle. If I don't put my origin in the center of my circle, my midline shifts up. And in fact, if I add a plus k to these, so now I'm looking at the functions y, a cosine plus k and a sine plus k. And these functions are going to have their midlines at the line y equals k. So, suppose, for example, we were given a wheel that is mounted through with its center, well, yeah. Four feet off the ground. And has a radius of 3 feet. We're going to label a point and we're going to label that point that is closest to the ground. And then we're going to spin the wheel. We're going to just label it P. And now we're going to spin the wheel. We're going to let it rotate. And what we want is to find a function that describes the height of that point. As the wheel is rotating. So, this is my circle. Remember that it's got a radius of 3. And the ground is down here. And it's mounted 4 feet off the ground. And what we care about is this point P. We are going to rotate our wheel this way. And I'm trying to describe the height of my function. So, let's do this. Think about my angle of rotation. And we're just going to write down the height of the point. So when we start, we have not rotated our wheel at all. And my point is 1 foot off the ground. Okay? Now, if I rotate my wheel counterclockwise, I'm going to make life easy on myself, and we're just going to go 90 degrees, so pi over 2. That gets me to here. So I've rotated to this point. Well, now my height is even with the center of my circle, so that's 4. right? Okay. And if I keep going, so if I get up to here, that means I've rotated 180 degrees, or pi radians. And my height is my 4 feet plus, so 7 feet. And if I were to keep going around, when I get to this point, I will have rotated 3 pi over 2 units. And my height is again going to be 4. And if I go 2 pi, I get back to 1. So sketching a graph of this, just make an XY plane. And remember, this is my angle theta on the x-axis. And what I am putting on my y-axis now is the height of my point. So when we started, we were at 1. When we went pi over 2, I'm just going to make that be pi over 2. We were at 4, so 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7. So now when I rotate to pi, this will be pi, my height, my point is 7 feet off the ground. 3 pi over 2, I'm back down to 4, and pi would actually be right, or 2 pi would be right here, and that gets me back down here to 1. So my circle, my path, my height of my point, remember this isn't the path of the point in space because that's a circle. This is the height of the point. Looks like this. So we can see that we start down here at a minimum and then we go over to maximum. So if we had started at a peak, this would be easy. We'd know it was a cosine. But we're starting at a valley. Well, our transformations will remember if we multiply by a negative number, it means we turn the function upside down. So my height is equal to negative something times my cosine of my angle plus something. Now, my midline is the center of my circle, so that's 4, right? And my amplitude is 3, so that's what goes in front. And that is the function that describes the height of my point. Now, so we have talked about adjusting or transforming the amplitude, and we've transformed the midline. The last thing we need to talk about is transforming the period. So think about if we were talking about time and we were rotating, so suppose we've got a point. Completes 1 revolution every 2 minutes around a circle of radius 5. And we want this time to find the x-coordinate. Of the point as a function of time. And we're going to say that the point starts at coordinates 5, 0. So I've got a circle. And it's got radius 5. And I'm talking about this point right here. It starts here. And we rotate my circle around. Now, here's what I know. I know that the thing makes 1 revolution every 2 minutes. So if we think about this in terms of time, at time 0, and what we're talking about is the x-coordinate of my point, the thing starts at 5, 0. So it starts with an x-coordinate of 5, right? If it takes it 2 minutes to go all the way around, then after 1 minute, we've gone halfway. Well, that's not very interesting. Let's try a quarter minute. So 30 seconds, 1/2 of a minute. Not a quarter of a minute, 1/2 of a minute. That gets me to here. So this is t equals 1/2. Well, now my x-coordinate, if I put my coordinate, my axes in, now my x-coordinate is 0. At 1 minute, my point is on the other side of my circle with an x-coordinate of -5. At 3/2 of a minute, my x-coordinate is again 0. And at 2 minutes, we're back at 5, which is what we expect because the thing completes 1 rotation every 2 minutes. So let's sketch this out. And my circle is again centered at the origin, so that will be my midline. So 0, 5, we're going to say that's 1. Let's spread those out. 1, 2. After 30 seconds, my x-coordinate is 0. At 1 minute, my x-coordinate is -5. At 1.5 minutes, my x-coordinate is again 0. At 2 minutes, my x-coordinate is 5. And if I sketch through these, curve begins to look like this. Right? Which looks like a cosine with amplitude 5, and that's what we expect. So my function of time, so we've got a 5 cosine, and that 5 comes from the amplitude, that 5 comes from the radius of the circle, right? But now, what is the period? Well, let's look at this. That's not what I want. My period, come on, quit. The distance between peaks is 2. And in fact, if we think about what we've got really going on here, because this is also, so this is a rotation of pi over 2, right? So this is how it ends up working. We need an internal multiplier in order to get us to our function. The internal multiplier is related to the natural cosine. So our observed period is 2. The natural period of a cosine function, the natural period of a pure unadulterated cosine is pi over 2. That internal multiplier is our observed, the natural period of sine and cosine are 2 pi. That internal multiplier is our observed period divided by the natural period, which in this case is, oh dang, I'm not doing good. That internal multiplier is the natural period divided by our observed period, which in this case is 2 pi divided by 2. So what we want in here is a 2, is a pi. So my final function is f of t equals 5 cosine pi t. So let's put this all together and wrap a bow around it. A function of the form f of t equals a sine of bt plus k, or f of t equals a cosine bt plus k, will be sinusoidal in shape, will have an amplitude of a, midline given by the equation y equals k, and period given by 2 pi over b. This is your big takeaway from this conversation of the transformations of sine and cosine. All right, there are several more examples in your textbook. I strongly encourage you to take a look at those and reach out to me if you have any questions. Talk to you soon.